we introduced some basic concepts and terminology to do with naming the various parts of the function. So a function went from a set x to a set y. The set x, where the arguments of the function come from, we call that the domain of the function. The set y, where the values of the function live, we call that the codomain of the function. Okay. Some of this terminology may differ slightly from terminology you've encountered before, but there is no universal agreement of how to use these words. They are used differently by different authors and so on, so just got to deal with it. We had the word image or range. The image or range of a function, we are using that to refer to the actual subset of values of the function, the subset of the codomain consisting of all the values of the function. All the elements of the codomain that the function takes. That may or may not be the whole of the codomain. If it is the whole of the codomain, that's what's called a surjective function. The function is surjective if every element in the codomain occurs with the value of the function. The other partner term with surjective was injective. Injective referred to, was it ever the case that the function sends different elements to the same value? If that is ever the case, if the function sends different arguments to the same value, then the function is not injective. It's many to one. It sends many values to the same, many arguments to the same value. If, however, that is never the case, if it's always the case that a value in the codomain is the image of one and only one, the image of at most one argument. So you never have two different arguments getting sent to the same value. If that's the case, then the function is called injective. And we looked at some examples of various combinations of functions that were or were not injective and surjective. Okay, and then something which we kind of rushed through at the end a little bit was the operation of composition of functions. So I just want to return to that now and say a bit more about that and look at some examples. So, composition of functions. Well, when can you do this operation? This is an operation that we perform amongst functions. And we can apply it when we've got a function f from some domain to some codomain y, and a function g, crucially, going from the same set y, this features over here, to some other set z. So f takes you from x to y, and g takes you on from y onto z. This is the situation where we can perform this operation called composition of these two functions. So here we can form a new function called the composition g and f, or more kind of everyday talk, locally, g after f. The symbol we use for it is a little circle, centralized circle dot. Okay, that's the composition operator. And it's a function that goes from the domain of x to the codomain of y. So to define a function, you have to state what its domain is, what its codomain is, and you have to say what all its values are. Okay. So this is defined by, well, for every x in the domain, g after f, this function applied to x is simply g of f of x. Okay. So you first apply f to the argument, that takes you into the set y. But when you're in the set y, you can apply g. Okay, because y is the domain of g, and that will take you on into z, codomain of g after that. Okay. So g after f, the g goes on the left, the f goes on the right, and that has this nice that f is nearest the x, so the f gets applied to x first, and g gets applied to x. But sometimes some people get slightly confused when reading this because you see the symbol g after f, but in g after f, it's important to note that f is the function that gets applied first, g is the function that gets applied second. And that can be slightly confusing because, at least in English, we have this convention that, you know, when you have a string of characters, the first character is the one on the left, the second character is the one to the right of that. However, when we're writing down composition of functions, we're not going left to right, we're going right to left. F is the first function in that composition. G is the second. Okay? So that can trip people up sometimes. Okay? But it is all arbitrary, this decision about whether the first thing in a set goes on the left or whether it goes on the right. It's just a decision. It's different in different languages, different situations. Okay? Some languages even go up and down the page rather than left to right across the page. So it's all completely arbitrary. What's important is we understand the conventions at work in any particular context. Okay, so that's the definition. We'll look through some examples. So, yeah, let's jump to these examples in example 3.4, and then I'll talk briefly about some other kinds of examples as well. Example 3.4 in your notes on page 26. So here we've got functions g, h, and r. Three functions g, h, and r. All of them are functions from the real numbers to the real numbers. So they can all be composed with each other in any order, can't they? Okay. Because the domain and codomain of each of them is the same, so we can glue them together in any kind of arrangement. And then the question there is, well, we have these formulas for them, so here I'm just copying out the question, just to get it all on the page. G of x is 2x minus 7, h of x is x squared minus 1, and r of x is exponential of 2x. So the question simply asks, obtain formulas for each of the following compositions. So the function g after h, okay, this is going to be a function from the real numbers to the real numbers. H goes from the real numbers to the real numbers, and then g takes you from the real numbers to the real numbers. So overall, you're going from r to r, and this will be defined by, okay, we want a formula for this, so we want g after h applied to x. We want to know what the formula for it is. Well, according to the definition of composition, this is simply g of h of x. H of x, we know what it is. It's x squared minus 1. So we want to apply g to x squared minus 1. You look at what g does to an argument. When you give an argument to g, it doubles it and subtracts 7. So we just do the same thing here. We double this and subtract 7. So we'll have 2x squared minus 9. Okay. Because doubling this gives us 2x squared minus 2. You subtract 7, getting minus 9. So this is the formula for g after h. H after r. So h after r, again, will go from r to r. And this is defined by h after r on an argument x. So this is all just the same. By definition of composition, that is exactly h of r of x. Which is, and r of x is e to the 2x, exponential of 2x. We then have to apply h to that. What does h do to an argument? You give h an argument x, and it squares it and subtracts 1. So we have to square that and subtract 1. Squaring e to the 2x will give us e to the 4x and subtract 1. So, I mean, you get the idea with these exercises. They're just getting you familiar with the concept and how to combine functions in different ways. Do this third example. G after H after R. Okay, so it's a triple composition. You'll notice that I haven't put any brackets here. I've just put the three functions down in a row. I mean, strictly speaking, that's a little bit ambiguous, because am I talking about the function? See, I've only defined how to compose two functions. So am I talking about composing G and H and then composing R? Or am I talking about composing H with R first and then composing with G? Which of these am I talking about? Well, I'm talking about both of them, okay? Because these are always the same. This is an important property of function composition. What's the name of this? Have you seen this? Anybody know the name of this property? Function composition is this property here. Sorry?
Commutative.
Not commutative. Commutative is the property G after H equals H after G. And is that true for function composition? No. Yeah. Function composition is not in general commutative. If you try and work out the formula of H after G, while we're on this point, let's do this. In contrast, H after G of X. And in some cases, it will be the same in some special cases, but I don't think that's the same here. And so what is H of G of X? This is H of 2x minus 7. And H, you square it and subtract 1. So we got 2x minus 7 all squared minus 1, which is whatever it is, 4x squared. Minus 28x plus 48. Okay, that is certainly different from 2x squared minus 9. Okay, so that example illustrates function composition is in general not commutative. It can be commutative for certain special functions. The functions are special in relation to one another, then they can commute with one another. But those are special cases. In general, we expect it not to be commutative. So no, but it's another word that's often spoken in the same setting as commutative. Do I know the term for this? It's associative. Associative. Associativity of an operation, like composition here. So this is a binary operation, meaning when we defined it at the top, it's an operation that operates on pairs of inputs. You give it an ordered pair of inputs, it tells you how to combine them in some way to produce the new composition function. Strictly speaking, you know, this thing is ambiguous. We haven't defined how to compose three things in one go. We can only do it by doing it according to the original definition. So either we compose G and H first and then compose with R, or we compose H with R first and then compose with G. But this property that these two are always the same, this is called associative, and this means by extension, once it's associative on three inputs like this, it'll be associative on any number of inputs. So I can write down a big long string of functions, composing them all in a certain order, and that'll be unambiguous. Okay? It doesn't matter how I choose to insert brackets into the thing to make it well defined on a pairwise evaluation basis. Well, whatever way I choose to evaluate it in pairs and build up to the big long product, I'll always get the same result. So most operations that we encounter in mathematics and study, you know, we're in trouble if they're not associative. If certain operations are not associative, it makes them very hard to study, because these two expressions will in general be different. So it makes them quite hard to study. But associative things that you're familiar with, so the the operation of addition of numbers, multiplication of numbers, whatever kind of numbers you want to take, integers, rationals, real numbers, addition of matrices, multiplication of matrices. Okay, although it's not, you've done multiplication of matrices in linear algebra, okay, that's an associative operation. It's not immediately obvious from the original definition of matrix multiplication that it is associative, but you can prove it is associative. Composition of functions, another one, important one that is associative. Okay, one way in the middle. I'm in the middle of trying to do this. Yeah. So, and really the proof that function composition is associative is really that whatever way you split it up, it ends up that the definition of this thing is simply g of h of r of x. I've opened three brackets, so I got to close three brackets. Okay. G of h of r of x. I mean, you could keep going all night with this kind of thing. So this is g of h of e to the 2x. Oh, h after r I already had there, so I could have worked that out. So this is g of e to the 4x minus 1. And then what does g do? G doubles it and subtracts it. So it's 2e to the 4x minus 9. While we're on the topic of composition of functions, just draw a connection to, and while we're making reference to multiplication of matrices, have you done the topic of linear transformations yet in linear algebra? So I think that's coming in a later section in the linear algebra. But I'll just make reference to it here, because it's an important example of composition. So in linear algebra, I'll just put this word in quotes, nice functions between vector spaces. I won't go into the precise definition of what nice is in this context. You'll do that in the linear algebra unit. But just to say, nice functions between vector spaces are called linear transformations. And given an n by m matrix A, given an n by m matrix A, this represents a linear transformation T of A, T for transformation, I just put a subscript A there because it's the one that's represented by the matrix A, and this goes from the domain Rm to the domain Rn. Okay, remember Rm is the set of all vectors of length n with real coefficients or components, and Rn is the set of all vectors of length n. So this is via the definition that if you apply the linear transformation to a vector x from Rm, it's equal to the matrix A multiplied by the column vector x1 up as far as xm. So that's what a vector x from Rm looks like this, column vector with n components. And if A is an n by m matrix, these will multiply together. Remember the rule for multiplying matrices. If you have n by m, and this is an n by 1 matrix, the dimensions of the product will be this n by 1 here. Okay. what you get out is a column vector I won't even bother to name them, but it's a column vector with n entries. So it's an element of Rn. Okay. So you've been looking at matrices already. You've been studying this operation of matrix multiplication. But one kind of meaning of it, or one way of interpreting what matrix multiplication means, is it's actually a way of representing functions from between vector spaces. Functions, nice functions between vector spaces, so-called linear transformations, ones that respect the vector space structure. Any linear transformation can be represented by a certain matrix. Now, the reason I'm bringing this in is that, there's a link here between composition of functions, the operation of composition of functions, which we're learning about here, and matrix multiplication, which you already know about from your linear algebra studies. N by one, n rows in one column. So how does composition look? Yeah. If we want to compose two linear transformations, TA, TB, okay? So let's say TA goes like this one from Rn to Rn, and TB, well, if we're going to compose them, TB is going to have to start in Rn and then maybe take you to Rs, some other vector space. If we want to compose these two linear transformations, then the composition, so by putting a B here, I'm saying that TB is represented by a matrix B. So this one is represented by n by m matrix A. This one is represented by a S. S by n matrix. S by n matrix B. Then the composition. So the composition we can perform here is TB after TA. Okay, that goes from Rn to Rs. Okay, this TA takes you from Rn to Rn. TB takes you from Rn to Rs. So this will be a new linear transformation. This will also be a linear transformation. And this is the point here that I'm driving at, that I'm trying to make. This will be represented by the S by n matrix, and it will be represented by the matrix product BA. Okay, remember B is n by m, A is n by m, B is S by n, so when you multiply them together, you get an S by n matrix. So, matrix multiplication connected very intimately. It kind of represents composition of linear transformations. Composition of the associated linear transformations. That's a good connection to draw between some of the things we're studying here and things you are studying and about to encounter in the linear algebra. And it kind of gives a bit of context to kind of the meaning of matrix multiplication. I mean, you've encountered matrix multiplication as an operation that you do amongst matrices, but maybe, you know, it's good to see some kind of an explanation of why it is the way it is and what matrix multiplication is represented. So it's represented as composition of these functions. Okay, so we've seen this operation of composition. We've seen some important properties of it. It is associative. It's not commutative. We've seen some examples composing various functions. We've drawn connections to linear algebra. So the other topics in the notes there are just a few more, bit more terminology and context to introduce. So we want to get to talking about inverse functions. So in order to do that, first of all, we'll talk about the identity function. So for any domain X, we have the identity function. The identity function ID defined on X by the rule, well, for every little x from the domain X, what is the identity applied to little x? Well, it's just X. Okay? So the identity is the special function, which is extremely conservative, just leaves everything the same. ID applied to the identity applied to X just gives you X. Okay? So it's a very boring function in some ways. Okay, just keeps everything the same. So now, strictly speaking, for for different domains, technically speaking, it's a different function, but we'll always use ID to refer to the identity function. Okay. So you might see in equations the ID appearing in various places in the equation, but in different places it might be representing a technically different function because it might be operating on a different domain. Okay. But that's just a sort of okay. So this has the nice property. This has the nice property that for any function f at all, and we won't bother to mention the domain and codomain of f, but there's this operation that you can compose f with the identity, and if you compose it on either side, you always get the same thing. What do you get? Well, remember, the identity does nothing in effect. It just takes an input x and it gives you x as the output. So if you perform the identity first and then apply f, well, an argument that you give to the identity, it just spits it straight back out again, gives it to f, and then you get f of x. Similarly, if you apply ID after f to an argument x, well, you give the argument x to f, it returns the value f of x. That's passed on to the identity, but the identity leaves everything the same. So the identity of f of x is just simply f of x. So in both cases, f of x comes out on both sides. So in other words, we haven't changed the function at all. Okay? When you compose any function with the identity, it leaves it unchanged. You always get the same function value. Okay? And think about the analogous thing that goes on with matrix multiplication. For any, well, at least for any square matrix, if we multiply it by the appropriately sized, what you call the identity matrix in linear algebra, that has the effect of not changing the matrix. Okay. Well, that's kind of the an instance of this kind of statement in linear algebra under the operation of matrix multiplication. And once we got the concept of an identity function, we can then define inverse functions. So if f is a function f from x to y, then the inverse of f is a function f inverse. So this superscript minus 1 is read as f inverse. F inverse, and this goes back the other way. So f inverse goes from the codomain of f back to the domain of f, satisfying f after f inverse is equal to the identity. Well, f after f inverse will be the identity function on y. If f inverse applies first, you start off in y, you come to x, and then you apply f takes you back here. If you always arrive back to exactly where you started, then this is the identity function of y to y. When you compose them the other way around, f inverse after f, that will give you the identity function as well, but the identity function on x. Now, but of course, not every function has an inverse. Okay. Okay, not every function has an inverse. Only the bijective functions have an inverse. Okay. F has an inverse if and only if f is bijective, meaning injective and surjective, or one-to-one and up-to. Okay. Okay, if the function is surjective and one-to-one, means you have this nice pair, the original function f from x to y is in effect a pairing between arguments from x and values from y, and they're just paired one-to-one all the time, and everything from y is paired with something from x, and everything from x is paired with something from y, and you never have two things in x paired with the same y, and you can never have two things in y paired with the same x because it's a function. It's just single value. Yes, question. Sorry? Oh, sure. I forgot the signage.
Oh, okay.
So we'll just forget that. Yeah.
Okay.
Okay. Sorry. Thanks very much. So inverse functions exist under certain circumstances. When the function is nice, when the function is bijective, okay? And you're familiar with this idea, you've seen this idea with matrices. Some matrices have an inverse. Those ones which have a non-zero determinant, okay? But not every matrix has an inverse. There's an example here, example 3.5. Of a real value function. So consider the function f from R to R. So this is defined by f of x is 2x minus 5. This is a nice injective and surjective function. Okay, you can realize any real value and express it as 2x minus 5 for some x. And secondly, you never get the same value out of 2x minus 5 for different inputs x. Okay? If you give different inputs x into this formula, you always get different values then. Okay, so it is injective as well. So this is bijective. So it has an inverse. And we can discover or obtain its formula by inverting the relationship so y equals 2x minus 5. See, y is the value of f which lives over here, x is the input to f which lives over here. We have this relationship that y is equal to 2x minus 5. Well, if we can invert this, then we'll know how to obtain x given the y value. So anytime it's possible to uniquely invert this kind of relationship, then there will be an inverse function. So you add 5 to both sides, and then you divide both sides by 2. Okay, so if somebody gives you a y, an element in the codomain R over there, this is how you get the corresponding x in the domain. It's y plus 5 over 2. So f inverse R to R is the function defined by f inverse of y equals y plus 5 over 2. Now we'll end by looking at Theorem 3.1, which tells us something very important about how inverses of compositions behave. So if f x to y and g y to z are two bijections, then so is the composite function g after f. So is that a bijection. So it has an inverse. And this theorem tells us that, well, the inverse of a composition, it does have a nice expression in terms of the inverses of the components of the expression, but there's an important fact to remember about it, is that you have to reverse the order. So the inverse of a composition is the composition of the inverses, but in the opposite order. Now you're familiar with this from matrices, okay? You've seen the matrix formula. So compare this with the matrix formula. Probably saw it like in this term, this notation: AB inverse is equal to B inverse A inverse. Okay, this is an example. It's kind of a universe. It's remember, composition corresponds to performing operations one after the other. So this corresponds, it's not a special mathematical fact really. It's a feature of the world. A nice example to illustrate it is, if you think of, okay, so every morning you get dressed, every evening you get undressed. Right? In the morning you get dressed. Okay, let's say you start off, you put your underwear on, you put your top layer of clothes on, then you put your coat on, and you go out for the day. You live your life for the day, and then you return home. Well, to get undressed, you have to take off the clothes, but you can't begin by taking off your underwear. Yeah, you have to begin by taking off your coat. You have to undo the operations, undo each operation, undo putting on each item of clothing, but you have to do it in the opposite order to how you put them on in the first place. Okay? So that's exactly what's happening here. To invert the operation G after F, you have to perform the operation G inverse first and then F inverse. You have to do F inverse after G inverse. Okay, then we've one topic left in this chapter, which is to just have fill in some of the blanks we left around partial fraction expansions. See that's at the end of this chapter. then there's also there's an extra section on at the end, which I realise now didn't print out properly. It's kind of incomplete as it is. But that's something I'll tell you about probably next week. It's a bit of just a fun topic to do next week, perhaps, or in one of the lectures in week 11 or that, just before Christmas. Okay, so for the tutorials, you can do basically any of the exercises in exercises 3.1, except for question 6 about partial fractions. Any of the ones about composition and inverses and so on, you could be working on for the tutorials. Okay, finish it there.